So when you want to lift something heavy, it helps to have what's known as a mechanical advantage, which means that I don't have to lift quite the entire weight that I'm actually trying to move. And in practice, what that means is that I exert a smaller force over a longer distance, and I do the same work as exerting a bigger force over a shorter distance. And one sort of familiar way that we do that is with a contraption known as a block and tackle. So if you were in Physics 8 last year, then you might have seen me use this contraption. So it basically there's one rope here, whereas the rope loops around 4 times here. So you'll see that if I want to move this end of the rope that has, the hook that has 4 ropes attached to it, if I want to move that 1 meter, I have to move this single end of the rope 4 meters. I'll zoom out in a minute and let you see what's up at the ceiling. And here, let me see if I can demonstrate that. I've marked, here's 1 meter, 2 meters. So I'm going to try to move my hand back and forth between this mark and this mark, which is 1 meter. And we'll see how many times I have to do that to get this thing to go up 1 meter. And it should be 4 times. So there's 1, 2, 3, 4. Okay, pretty good. So this hook went from here up to here, which is a 1 meter travel for the hook. And to achieve that, I pulled this single rope 4 meters. And what that means is if we attached some weight here to this hook, then I would not have to lift that entire weight. I would only have to lift 1/4 of that weight. And if that's a mass m and it goes up some change in height h, then I'm doing some work mgh, and I do that same total amount of work but with a smaller force because I'm exerting 1/4 of the force, but I'm traveling over 4 times the distance. And you say, how would you use that? So one way I would use this mechanical advantage is we've got this pretty large box here. It says 116 pounds. What is that? That's, let's say, roughly 50 kilograms. And there's just no way I can lift this thing. Well, I guess if I really try, I mean, I can lift my 85-pound dog, so maybe I could just barely lift it. But basically, to a good approximation, I can't lift that. However, if I hook up this 4-to-1 block and tackle, then instead of 116, instead of say 50 kilograms, I only have to lift about 13 kilograms, which seems doable, right? So instead of 116 pounds, that's like 29 pounds. So let's see if I can do that. Gee, it's still not exactly easy. This is definitely much more difficult than I remember, but I guess I can sort of do it. I think I have the coronavirus reduced muscle mass. Let's see. Whoa! Okay, well, you see it went up in the air a little bit, although, gee, not a whole lot. Wow, I think this must be more than 116 pounds. You can see that what's attached to the ceiling is basically, well, it's a classic block and tackle. You can look up block and tackle in the Wikipedia, and here's the bottom part. It's basically like a couple of pulleys with ropes looped around multiple times. And again, the idea is that you move the single rope 4 times as far as the group of 4 ropes moves. And that way you can exert only 1/4 of the force on the single rope that's exerted on the set of 4 ropes. Let's see. Well, I guess we could see what it weighs after picking it up. But you see, it's going to be more than, it's going to be like 600 pounds, because like 150 pounds won't offset it. You want to try one into this?
Sure.
Just make sure we don't. Oh, look at that.
There we go.
All right. Mechanical advantage. That's right. Okay. We should try to weigh it.
Yeah, I brought this out, but now
I think it's going to go off scale.
I'm just curious if I can get this in a spot.
Where we can read it still.
Yep, I'm sorry.
All right.
Yep, I can still read it when it's there.
Okay, then
And so if you can lift it, I'll slide it.
we need the girl power too.
Oh yeah, good call.
All right.
My goodness. Oh.
Okay, let's see.
Right,
Can you still see the dial?
Right. Oh yeah, it like rotated all the way around.
Okay.
It's at least 280 pounds.
Yeah, because that's 300.
That's 300.
And then it goes, it's probably like 400 pounds.
Oh my.
So this thing turns out to be 218 kilograms. We found a scale big enough to weigh it. So that's about 500 pounds. So it's no wonder I couldn't lift even a quarter of it, because even a quarter of it is just a little bit less than, so if I really were able to hang down with my 150 pound weight, I should be, well, you can see that I made it lift a little bit by putting my whole weight on the other end. So I put my whole 150 pound weight on the other end, and with some effort I got it to budge. But you can actually make something ginormous lift up much more easily with the help of a compressed fluid. It's actually a lot easier if you use a confined fluid, and we'll see how that works in a second, but you can see I'm exerting just the tiniest bit of force on the end of this handle, and it has no, now it doesn't have to pick up the whole weight, it has to pick up about half the weight, if you remember torque from last year, because I've got it supported on one side and I'm lifting it on the other side. But still, you can see, even lifting half of this weight is like zero effort at all. I mean, not zero, but extremely easy. This basically 500 pound, 218 kilogram block using the confined fluid. While we're here, so I guess the idea is, I go up a little bit, so I think it's not exactly 4-to-1, but it's close.
Well,
So,
you can go up with just a wonder.
yeah, but I can lift myself up, so I only have to pull a quarter of my weight to do this. Of course, if I let go of it, then it's going to hurt. But, yeah, but here, I can start near the floor. You can see me. So I only have to pull a quarter of my weight to lift myself up. These gloves are kind of slippery. It's actually probably safer without the gloves.
Yeah.
Yeah. All right. So even with the pandemic loss of muscle mass, I can easily lift myself up. All right. Let's try something a little bit less death-defying. Here is 25 kilograms. So a little over 50 pounds, 55 pounds, I guess. So I can lift that, but it takes some effort. Now, if I connect Mr. Block and Tackle, then again, you see, every time I pull this down a meter, the 25 kilogram block goes up only a quarter of a meter. So I pull this thing down 4 meters to get that to go up. See, now it's a meter off the ground. 1, 2, 3, 4 more. Now it's 2 meters off the ground. So instead of having to do the force equivalent of 25 kilograms, which is about 250 newtons, I only have to pull down with the force equivalent of 6¼ kilograms, which is about 62 newtons. Or to put it in pounds, so instead of having to pull down with a weight with 55 pounds of force, I only have to pull down with a force of, so 12.5 plus 1.25, about 14 pounds. So I only have to pull down with a force of about 14 pounds instead of a force of about 55 pounds. So that's a mechanical advantage. Meanwhile, we're going to try to figure out what the weight really is of that ginormous. Okay, so again, actually, just while we get it here, it's just too much fun. So it's on the ground. So if I were to get it 1 meter off the ground, I'll go 1, 2, 3, 4 meters. Good. 5, 6, 7, 8 meters. So I pull the rope down 4 meters. The big weight goes up only 1 meter. I pull the rope down 8 meters. The big weight goes up only 2 meters. That's a 4-to-1 mechanical advantage. So instead of having to lift 25 kilograms, effectively I'm lifting 6¼ kilograms. Or basically, instead of lifting about 50 pounds, instead I'm lifting like about 12.5 pounds. So now the question is, okay, that's a 4-to-1 mechanical advantage, and you can find a block and tackle that'll get you like an 8-to-1 mechanical advantage maybe. But what if you want like 1,000-to-1 mechanical advantage? And I'll tell you why this is relevant. My dad and I once lifted up part of my house to replace a failing beam. So then we really had to lift up an enormous amount of weight. And you say, how would you do that? How in the world are you going to get a mechanical advantage that's like something like 1,000? Well, one way you can do it is with an incompressible fluid, which is forced to stay in a fixed volume. So if you have an enclosed incompressible fluid, then if you push on it one place, then the resulting increase in pressure is distributed throughout the fluid. That's Pascal's principle. Or actually, all you really need to know is that the fluid is incompressible. So that means it takes up the same volume all the time. So then, if you are if you're kind of forcing it through a volume one place, that same volume of fluid is going to come out some other place. And here, I'll just cut and restart, and we'll see that. Okay, so you saw with the mechanical advantage of 4 that I was able to lift up this 25 kilogram block without too much effort. Certainly a lot easier than the 220 kilogram monstrosity. But then I can show you that if you want a much bigger mechanical advantage, notice that if I crank this thing, let's see, if I go down, I'm going to go down, there's from about 30 centimeters to about 5 centimeters. I'm going to go down about 25 centimeters. And meanwhile, this thing seems to go up only a few millimeters. Let's see if we can measure that. So I'll do it 10 times. So now we're pretty close to 20. Well, let's see. We'll start at about 20 centimeters. I'll go 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's about 250 centimeters. Actually, I'll go another 10, that'll be 500 centimeters. How about that? So then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I went about 500 centimeters downward because it only compresses the fluid when it's downward. And meanwhile, this thing went up by, oh, okay, we started at 20 centimeters and now we're at about 28.5 centimeters. It's about 8.5 centimeters. Actually 500 divided by 8.5. So that's like a mechanical advantage of about 60. So then this 25 kilograms, essentially I only have to exert the force of less than half of a kilogram. So let's try that. And then maybe we'll talk about what's going on in here. So you can see this thing is a little more than 50 pounds, about 25 kilograms. And, oh, gee, that's annoying. It's got a, the bottom is here. Okay, that's good. So now you can see it takes, basically, I mean, I could do it with like one finger. It basically takes negligible effort because the force I have to exert on the far end of this handle corresponds to about 1/60th of this weight. So, okay, and then you see I can make it go down. And then I can lift it back up. Right, so this is about a 60-to-1 mechanical advantage. And I think I haven't tightened it completely, so it's leaking a little. You even get a slightly better mechanical advantage with the larger one. So we just saw that with the small, this thing is rated for 2 tons. This is a 2-ton hydraulic bottle jack. And I just estimated a 60-to-1 roughly mechanical advantage because I moved this thing 500 centimeters and this went up about 8.5 centimeters. So that's roughly 60-to-1. Now one thing we can do is we can compare the 2-ton bottle jack to the 6-ton bottle jack. And I think what's happening on the input side is the same in both cases, but on the output side, in one case, you have about a 2-centimeter diameter cylinder. In the other case, we have about a 3-centimeter diameter circle. So that's about a factor of 1.5 in diameter, which is a little more than a factor of 2. What's that? A factor of 2.25 in cross-section, and I might not have measured perfectly. Because you might think, well, maybe you actually expect a factor of 3 to go from 2 tons to 6 tons bottle jack. But then I think we can see, actually, maybe the best way to measure that ratio, if we
Crank each of them a dozen.
if we crank each of them, let's say 20 times. Here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We'll do 20 times on this one. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Then this one moved by, well, we'll measure just the exposed metallic colored part. So this was, yeah, a little over 8 centimeters. Okay, maybe, yeah, 8.1 centimeters. And this is about 3.4 centimeters. 8 divided by 3.4 is, how about that, 2.35? That seems consistent. This one moved up by about 2.35 times as much as this one went up. And that kind of made sense because we measured the diameter of this circle, and it was about 2 centimeters, and the diameter of this circle was about 3 centimeters. So we said, okay, 1.5 squared is the ratio of the areas, which is about 2 1/4. And then we said, okay, the ratio of the distances of travel should be about the reciprocal of that. So this is about a factor of 2.35. So you're pushing, each time you crank this up and down, you're pushing a fixed volume of, you're moving, displacing a fixed volume of fluid, and that fluid is coming out the other end and it's pushing this cylinder up. And you can see that basically the cross-sectional area of this cylinder times the change in height has to be equal to the volume of fluid that you displace. And this is a larger cross-sectional area, so it's going to take a smaller vertical displacement for the same volume of fluid. This is a smaller cross-sectional area, so it's going to take a larger volume, larger vertical motion to displace that same volume of fluid.
Okay, we're going to talk about an interesting problem in many of your physics books. The problem states that there's a person in a small lake, in a canoe, and he's got a very large boulder in the canoe. And so the canoe is floating, so he decides he's going to throw the boulder over the edge of the canoe. So he does this. The question is, what happens to the level of the water in the lake? There are three possibilities. This is kind of semi-qualitative. We're not going to ask for numbers. But clearly one option would be that nothing happens to the level of the water in the lake, and it just remains as it was. But it's also possible that the water level rises, and it's possible that it goes down. And so the first thing to do is for you to think a little bit about this and write down your choice. Now, don't just say in your head, because then you can kind of hedge your bets. Put it on paper so you got to live with it. So what do you think happens if we throw the boulder out of the canoe and we're keeping track of the lake? Now, many of you are going to say nothing because you've seen such things happen and nothing happens. And the problem, of course, is the lake is huge. The boat and whatever's in the boat, and maybe it's another person who jumps out, are pretty small. Well, we're lucky today. We're lucky that we have a really small lake. Look at this. This is as small a lake as you can get, and a really big canoe. The canoe is almost as big as the lake. And if you notice, when the canoe goes in the water, okay, and have you thought about what floating is? Floating needs buoyancy. And what is buoyancy? Buoyancy is the effect that the water doesn't want to get out of the way of an object that's placed in the container. And so if I am going to push this boat down, the only way for it to go down is for the water to get out of the way. And the only place for the water to get out of the way is to go up the sides. And for you fans of potential energy, what's happening here is we are giving the water potential energy. We're also lucky in that we've got a boulder. Our boulder is a 5 kilogram mass that just fits into our boat. And so now we're going to put this, and let's keep track of this whole operation. So we've got masking tape. So unlike your lake, and maybe you could do this with a lake by taking a stick and marking the sand at the shore. So this is pretty much the level of the water. And so we're going to take our boat and put it in our lake. And here's our boat floating in the water, and look at that water level. It really changed. So let's mark it. So what just happened here? Well, the canoe and stone pushed water down, and the water went up. Now, why didn't it push any more down? Well, it turns out it had to lose a certain amount of energy to get down here. That's all the energy it's got. If you think about it, once this thing gets underwater, obviously it doesn't have to move any more water, but it only had enough energy to move this much water. And so we've now got an equilibrium. The lost energy in the height of this equals the gained energy here. If it turns out that the water energy is less than our device here, the displacement of the water, then it floats. And of course, the energy is, potential energy is mgh, but the g is the same for everybody. And so it turns out that we are going to displace an amount of water equal to the weight of the object. And if it turns out that the object takes up more room than the water that matches its weight, it's going to float. Because now this guy goes in, it pushes that much water out of the way. Here is the weight of the object. The object still has some volume. Let's emphasize the point briefly by getting back to a very light canoe. So we take our boulder out, and now we notice that the water level is awfully close because this is just made out of plastic and it has almost no weight. And so water is pretty dense stuff, and so it only takes that much water to match its weight, and it's just hunky-dory. So now we're going to take 5 kilograms of cast iron, put it back in here, and that means we've got to push 5 kilograms of water out of the way, which we've just done. And that's as far as we're going to go. So now we've kind of given away a lot. We'll even give you the opportunity to change your answer before we do it. So we're going to take the boulder out, throw it into the lake, and take a look at the water level. Okay, our lake is so small that we're going to have to get the canoe out of the way in order to throw the boulder in. In it goes, in goes the canoe. Woo! So notice it's very much lower than it was. The canoe is still floating. But of course, the only displacement we have now, we are displacing water equal to the size of our cast iron. The cast iron is really dense, as 8 times as dense as the water. And so it takes up very little space. What we have done with the boat is essentially given it more volume. And so now we've got that same mass, that same amount of gravity, but now in order for it to move through the water, it's got to push a lot more water out of its way. And so we're getting volume from the container, and we're getting mass or weight from the boulder. And so think about what went on here, because this is at the core of what buoyancy is. Buoyancy is the force, this water that's been raised up, just like anything that's been raised up, now has potential energy and it's delivering a force. So it's pushing back. It's trying to get into that space we just pushed it out of with an effort equal to the gravity acting on.
Sir, are you saying that in one case you're displacing a volume of water whose weight is the same as the weight of the boulder? And in the other case, you're displacing a volume of water whose volume is the same as the volume of the boulder?
Well, right, and this is what we have to be careful with. If we've got the boulder, we go in and we displace an amount of water equal to the volume, because it turns out this weighs a lot more than that water. But if we give it more volume, now we displace an amount of water equal to its weight, and then we're done. Because once we match the weight, we don't have an effort sufficient to push any more water up. I can do that manually by pushing down. I can get the water all the way up to the top and get it to overflow, and then we got to clean up a mess, so I'm not going to do it. If I lift this up, clearly the water doesn't have to support as much because I'm supporting some. But if we just let the water and the gravity of the system come into equilibrium, here's our water level. And so the question is, what is the controlling variable? If the density of the object exceeds that of water, the controlling variable is the volume of the object. It goes in and pushes that much stuff out of the way, and then the water's done working. If the density is less than water, then the controlling variable is its weight. And as it goes in, it pushes water out of the way until the moved water matches the weight of the object. So let's take another example where, okay, boom. All right. So what's in here? Okay, is it Windex? Is it blue gate? No, it's just water, and we have put blue dye in it in order that you can see this water when it's in this water. And so you can see this is a water bottle that's not completely filled. And so the question A is, will it float? And I'm hoping most of you are going to say, yes, it will. But then I'm going to say, how will it float? Is it going to be right at the surface? Is it going to float with something sticking out? Can we get more specific? You're thinking about it, right? Here we go. In it goes, it keeps going down, and look at where it stops. Now it turns out that it's more stable lying on its side, but it almost doesn't matter. Because if you notice, it stops at a point where the blue water lines up with the clear water. If it's vertical, it does it there, but if it tips over on its own, once again, the blue water lines up with the clear water. And so what does this mean? Well, it means that we've just verified the statement we made about the canoe and the boulder. And that is, we push water out of the way until we've pushed the weight of the object in water out of the way. And how much water is that? Well, if the object is water, we have to push an equal volume of water. So this thing is going to sink in here until the volume of the blue water has been displaced and the water has raised that level. It's a small amount next to our tape, but we can clearly see how much of the bottle remains above. I know some of you clear thinkers out there are saying, but what about the bottle? And I'm saying this is one of those cheap water bottles that's a really thin layer of plastic, and its weight is of almost no consequence in this behavior. And so it gives us almost a water balloon to play with here, but it's rigid enough to have volume without water. Okay, we got that? So we're ready for the central discussion. We get the...
You're also saying water seeks its level.
That water seeks its level, yes. And of course, once again, if you chase that down, it's going to be a potential energy problem. It's the reason that you don't have a pile of water anywhere in the ocean. And it's the reason that absent a wave, you can't water ski or surf. Because any pile of water has to be a dynamic situation. It can't be static. You get a pile of water anywhere, and of course, it's got more potential energy than the water over here, and it will quickly come down and push that water out of the way until all the water has the same potential energy and everybody's at the same height. So water makes for a very nice device to check on levels. So now that you know everything there is to know about buoyancy, I'm going to pose you a real challenging question. We have here, and we've carefully chosen generic brands, so we've got generic cola and generic diet cola. If we take a look at them, they each tell us that there is 355 milliliters in each can. You will recognize that as 12 fluid ounces. So we are now going to put these respective cans into this water. Once again, there's a hollow in the bottom. And I'm going to put the cans in sideways to make sure we don't catch any air in those hollows. So we're going to put the regular soda in here. So in it goes. And bingo. And how many of you would have said this won't float? So the cola can is down there on the bottom. So why would cola sink? Well, of course, if you read the ingredients, the first ingredient is water. It's almost all water. So shouldn't it be like neutrally buoyant? Well, sure, but there's an aluminum can there, okay? And so we've got a hunk of metal attached to this water, so we can come up with a pretty good hypothesis for why it doesn't float. So in goes the diet cola. Whoa, how about that? Now, have we discovered something important? So let's come up with a hypothesis for why this floats. So if you shake it, there's a little air bubble in there. It isn't absolutely full. There's some airspace. And so there's airspace in here. There's aluminum there. It turns out that you could probably argue either way. Is there enough air to balance the aluminum? Well, this would seem to say that there is, but that would seem to say that there isn't. So can we come up with a consistent answer? What's different? Along with the fact that one floats and one sinks, what's different? Well, we might want to take a look at ingredients. And it turns out, and we don't even have to look at ingredients, we just have to look at the now mandated calorie content. And clearly the diet cola, unsurprisingly, has 0 calories. The regular cola has 160 calories. And that's something you gain with generic soda. It tastes so bad they have to give you extra sugar. Coke has just 140 calories, Pepsi is 150, generic is 160, and of course it's all sugar. And so the big point is, there's more sugar here than there is here. If you dissolve sugar in water, you create a solution with a higher density than water. And so it turns out that the density, and let's remember that water is really the central object in density. The definitions in the metric system are related to the density of water. Water defines all of this stuff by having a mass of 1 gram per cubic centimeter or per milliliter. So a density of 1 is water. Things sink if they have a density more than 1. Things float if they have a density greater than 1. These two are close. We know one of these floats and one sinks in a fluid of density 1. What if we changed the density of the fluid? Well, clearly if the fluid is air with almost no density, they both sink because they sit nicely on a tabletop or a countertop. But we can change the density of this by dissolving something in our tank of water, because we've proposed that the density of the liquid in the can is related to how much sugar is dissolved in it. And so we have got some salt here. You say, why don't I use sugar? And the answer is because it's sticky. And so we've just got regular salt, okay? We're gonna, now let's take note, and I actually had a student a while back who really kind of embarrassed me. I put in the salt and stirred it up, and things changed. And the student said, well, how do you know that that change didn't come about because you stirred it? And they were totally right. That was a bad experiment. You don't want to make 2 changes at once. So let's start by doing nothing but stirring and see if the cans care. And so we're stirring our little hearts out. The cans are swirling and staying right where they were a minute ago. So apparently stirring's not much of an issue. So now we're going to add salt. And I can see some changes beginning to happen. One of the changes, and if you want to take a look at both of them, it turns out, because we think we're raising the density of the fluid, so our prediction would be we ought to be able to make the denser one float, but also that the less dense one should float higher. In other words, if the water is more dense, you don't have to move as much of it to match your weight. So let's stir this up. And we're getting close. That guy on the bottom is not touching the bottom much. And you note the one at the top is beginning to float high enough that it's tilting. So we add a bit more salt. Now, if you have been swimming in a saltwater body, like the ocean, like the Great Salt Lake in Utah, the Dead Sea in Israel, it is much easier to float, because if you have salt in the water is denser and things don't have to move as much water out of the way. So we're pretty close now. You can see that we're no longer touching the bottom with our original can. And bingo, it's now riding up here at the surface. But it's not hard to continue to realize that the regular sugar soda is denser than the diet, because the diet soda is floating higher, and so it is a lower density. But it is a very interesting accident that the densities of 12-ounce cans of soda are so close to matching the density of water that we can do something like this with minor changes and see major differences. Hi again. Now that you're an expert on buoyancy, we're going to take a look at what you thought was a simple problem. Look at that. Right, we have a bubble gun. So what's a bubble? Well, it's air, right? It's this little bubble of air. But you're noticing it's sinking. These bubbles are dropping rapidly. Now, why is that? Is there a good reason? Like, it's air. Why doesn't it just hang with the rest of the air? And of course, you're probably thinking, well, yeah, but it's got a container like that soda did. Now, it's not an aluminum container, but it's water and soap, which is clearly more dense than air. And so the combination of a sphere of air and a thin shell of water is more dense than the sphere of air that's the size of those two guys together. And so consequently, our bubbles succumb to gravity relatively fast. Now, what we have here is an aquarium. And it's full of a fluid like any aquarium. It's just that this is a less interesting fluid. It's full of air. And bingo, we can watch bubbles do their bubble thing. And it doesn't matter whether they're in or out. Gravity is still in charge. But what if we fill it with something else? What if we take you back to grade school and that great volcano experiment you did where you put vinegar and baking soda together? And this is a complex thing. We got vinegar here, we got baking soda here, and you know, we're doing chemistry, so it's really important to measure carefully. And this is foaming its little heart out. Now, do you remember that volcano experiment? Can you tell me what's bubbling? Like, where'd these bubbles come from? What's happening? We clearly need a little more vinegar, a little more baking soda, and it's frothing away. It turns out it's CO2. And for you folks who actually stayed awake in chemistry class, air is N2 and O2. Both of those are quite similar in terms of molecular weight. CO2 is O2, obviously, with a C hooked up. And so it turns out that CO2 is denser than air. And so we've generated CO2, but because it's denser than air, it's really not flying out into the room, it's sitting here. And so if we take our bubble gun and we shoot some bubbles, it looks like we have stopped gravity in the container. I mean, these guys are like hanging there. Let's get him out of the way so you can see that there is a bubble that does not care about gravity. Well, it actually does, but it cares about a combination of forces. And so it's got the same buoyant force that our bottle did in the water. The level of CO2 is right around here. Now you say, well, why aren't they floating at the same height? Well, they're two different sizes, so there's two different amounts of soap. But there's another interesting thing that happens. It turns out that the soap film is a semi-permeable membrane, and the oxygen and CO2 can actually migrate. So with time, these guys begin to sink because we get a little CO2 drifting in and a little O2 drifting out. But now that we fully understand why things float, this isn't magic anymore. And we can find the level of the CO2 in the container. This is a fun experiment to do. You can do it, it's grocery store stuff. It's a bubble gun, it's vinegar and baking soda. Important point, the container needs to be almost a foot in any dimension, because if it's smaller, static electricity generally messes you up and the bubbles find an edge and don't hang in the middle. And glass seems to be less prone to static electricity than plastic. But this is worth doing, huh? I mean, mess up your house. You're stuck there anyway, and you can actually do some neat science.
So we have here a 1 kilogram block of aluminum. It's actually a cylindrical block. And right now it's just hanging in the air. So all of its weight, if it's 1 kilogram, its weight is 9.8 newtons. So all of its weight is being held from the top now. So you can really see the full 9.8 newtons on this scale. Now this scale reads newtons. Unfortunately, this scale down below reads kilograms, so just bear that in mind. And we have zeroed made the tare adjustment on the scale, so we've zeroed it out so that the weight of the water itself does not show up. So now I guess we can use the principle of Archimedes, and if we wanted to, we could infer the volume of this block of aluminum by seeing how big a buoyant force is exerted by the water when the aluminum is fully immersed. So let's give that a try. So we will gradually lift up the water to meet the aluminum, and we'll see that as more and more of the aluminum is immersed in the water, we'll see the weight carried by the water, or the force exerted by the water, basically, on the aluminum will go up, and then the force exerted by the upper support will go down. And remember, these scales are a factor of 10 apart. So it's gone down from 9.8 newtons on top to about 6 newtons. Okay, actually, you see now it's not changing anymore. So now the aluminum is completely immersed. That's actually kind of neat to step back and see. So you can see that when we're partially, so we're not immersed at all, and we read our 9.8 newtons here, basically. The precision of the mechanical scale is a little bit, it's not ideal. We're going to repeat this with a digital scale in a moment. But you get a nice visual impact here. So as we immerse more and more of the aluminum in the water, you see that the fraction of the aluminum block's weight carried by the upper scale is reduced, and it's made up by the weight carried by the water, the buoyant force of the water. And the buoyant force of the water is then transmitted down to the ground through the scale. So if we get to the point where we are completely submersed, then of course it doesn't matter whether we continue to immerse it more and more. Of course, if you eventually reach the bottom and keep going, then everything will be held by the bottom of the jar. But we want the buoyant force. So it seems as if when the aluminum is fully immersed, in the water, it looks as if instead of about 10 newtons, we have about 6.4 newtons red on the top. So that means we should have something like 3.5 newtons down below. And indeed, this looks like 1, 2, 3, about 3.5 little ticks. We know that the buoyant force equals the mass of the displaced water. And we know that the mass of the displaced water must be about 0.35 kilograms, since it's whatever water has a weight of about 3.5 newtons. And I guess that would let us infer the volume of this block. We know its mass, we know its volume, so we can infer its density. And it should check out to be the roughly 2.8 times the density of water that we expect for aluminum. So I guess we could give that a try. Okay, so we have the mass is 1.0 kilogram, and then the weight is 9.8 newtons, and then we have the buoyant force seemed to be about 3.5 newtons, and that should equal the density of water times G times the volume of this block. So that lets us say that the volume of the block is 3.5 newtons divided by the density of water, which is 1,000 kilograms per cubic meter, and then times little g, which is 9.8 newtons per kilogram. Yeah, so this is going to be an absurdly small number of cubic meters, but basically it's going to turn out to be 0.35 liters. Yeah, if you put it in liters, it's basically 0.35 liters. Yeah, and then if we say, let's check that the density seems to come out about right. So we can say, okay, then the density of the block would be its mass of the block divided by the volume of the block, which is, so now this whole thing goes up, is turned upside down. Yeah, so there's 1 kilogram, 1.0 kilogram. And I think we're going to find a big cancellation here, and we'll have 1,000 kilogram per cubic meter. Okay, 1,000 kilogram per cubic meter. And then we'll have 9.8 newtons per kilogram. And then downstairs we'll have 3.5 newtons. Right, so we get a whole bunch of tens divided by 3.5. So it's going to turn out to be a density of roughly 3 times the density of water. Here, if we try just doing all the multiplication, let's make sure that works out. So first of all, if we did the multiplication up top, even though it's going to be a ridiculous number, there's 3.5 newtons divided by 1,000 divided by 9.8. So you get, right, whatever number of, there's 0.35, 0.35 times 10 to the minus 3 cubic meters. 0.35 times 10 to the minus 3 cubic meters, which is 0.35 liters, so that makes sense. And then if we take this, we've got 1 kilogram times 1,000 kilograms per cubic meter times 9.8 newtons per kilogram divided by 3.5 newtons, and we get, right, 2800. So remember, in SI units, densities are like water's density is 1,000 in SI units, so you get 2800 kilograms per cubic meter. So that's 2.8 times the density of water, which I think is the right answer for aluminum. Let's see. So if we say density of aluminum, it is, okay, 2.7 times the density of water is the accepted value. We got 2.8. We're going to repeat this with a digital scale, and maybe we'll see if we get a little closer. But you see the idea anyway. So the buoyant force is the weight of the displaced water. Okay, let's go back to our 1 kilogram block of steel, and we can weigh it with our digital scale. And we get 9.80 newtons. Then, let's immerse it in water. And you can see the weight held by the top support goes down as we immerse it more and more. And then once it is fully immersed, then this reading doesn't change anymore. Okay, so now we have 6.45 newtons. So we can subtract and we get 3.35 newtons. So then to speed things up, so we know the specific gravity is just the weight of the object divided by the buoyant force. So that will give us the specific gravity is just the ratio of these two, 9.80 newtons divided by 3.35 newtons. So this should work out to be the density of steel. So 9.80 divided by 3.35, that's not going to work out to be the density of steel. Oh, it's aluminum. Ha! 2.92. This thing is obviously not steel, it's actually aluminum. Ha! Okay, so now we're going to try a different trick. We're going to say, instead of weighing it in water, let's weigh it in glycerin. Or maybe we're weighing it in a mystery fluid, and it'll turn out the mystery fluid is glycerin. Okay, so here's our aluminum cylindrical block. It's 1 kilogram, 9.8 newtons. And now, instead of immersing it in water, we're going to immerse it in, well, we think this is glycerin. And we think glycerin probably has a density about 1.25 times the density of water, but let's just check that out. Let's see if we can see. So the buoyant force should be about 25% larger in glycerin than it is in water because the density of glycerin is higher. So the weight of the displaced glycerin is bigger than the weight of the displaced water. So let's try it. So we will immerse it in the mystery fluid, which is glycerin. And okay, it's just about to make contact. So we still have 9.8 newtons. I don't know how 9.8 became 9.7. And okay, you can see it's going down, it's going down, it's going down. And now we are completely immersed. So we're down to 5, looks like, well, okay, seems like 5.5 roughly. See, if we keep immersing it more, it doesn't change the answer anymore. So we're fully immersed. So it seems like we have, well, it looks like 5.50 newtons roughly. We had 9.80 newtons minus 5.50 newtons. This difference. And so this is going to be our buoyant force. This is the F buoyant in glycerin. So there's 4.3 newtons. Instead of 3.35 newtons, now we have 4.30 newtons, roughly. It's a bigger buoyant force. 4.30 newtons. And, you know, we don't have to do a whole lot of work here. We could say, okay, F buoyant, we know that F buoyant must be the density of glycerin times little g times the volume of the block. But we don't have to do all that work because we know the density of water is, well, the specific gravity of water is 1. Its density in SI units is 1,000 kilograms per cubic meter. So I say, okay, water is 1. This buoyant force is 4.3 newtons compared to the buoyant force of 3.35 newtons in water. If we take the ratio of these two numbers, that should be the density, that should be the specific gravity of glycerin. The density of glycerin divided by the density of water. So let's try that. 4.3 divided by 3.35, and we get 1.28. So, okay, so you say F buoyant in glycerin divided by F buoyant in water. So remember, this is the density of glycerin times little g times the volume. This is the density of water times little g times the volume. Little g is the same, v is the same. So this is just the ratio of the two densities. So the ratio of the, so this is 4.30 newtons divided by 3.35 newtons is, again, 1.28. So, okay, so we decided the specific gravity of our mystery liquid is 1.28. It should be 1.28 times the density of water. And the accepted value for the density of glycerin, the specific gravity of glycerin, is 1.26. So that seems, so it's good to 2 or 3 significant figures. I guess that kind of makes sense because we probably believe that we measured things to about 2 significant figures. So, good. Okay, let's play Archimedes with the digital scale. So we have here, well, you know, in the real lab version of this, you have to infer what the material is. But let's just say I have a pretty good hunch that this is going to turn out to be steel. And I have a pretty good hunch this is going to turn out to be aluminum. So let's see what happens. So this readout is reading the weight supported by this little hook. So if I take this large unknown material, nut, and I suspend it, then we can say what is its weight when it's just in air. So it's just being suspended entirely by the hook. And its weight in air is let's say 1.61 newtons. M, nut. G is 1.61 newtons. Now, we have water down below, so we want to say we can measure its volume, we can infer its volume by measuring the buoyant force of the water on the nut when it's fully immersed. So let's do that. So we're going to lift the water up to immerse the nut. And we should see that the weight held by the upper support gets smaller and smaller and smaller as I immerse a larger and larger fraction of the nut. But then once the nut is fully immersed, then continuing to immerse it to a larger depth won't change the buoyant force. So the buoyant force plus the force held by the upper support together add up to the actual weight, the weight in air of the nut. So you can see that as I continue to, if I change the depth at which it's immersed, as long as it's fully immersed, then this buoyant force doesn't change. Of course, it would change if it hit the bottom, but we're not going to do that because then it's not a buoyant force anymore. Okay, so we have 1.41 newtons. So we don't get a whole lot of digits out of this, but 1.41 newtons. So this is the weight in air. And then we have 1.41 newtons is the apparent weight when immersed. In water. So that lets us infer, so we just subtract these two. So if you subtract, you get 0.20 newtons. So the buoyant force is 0.20 newtons, and that equals the weight of the displaced water. So that is the density of water times little g times the volume of the nut. So then we can infer the volume of the nut. So then the volume of the nut equals F buoyant divided by the density of water and also divided by g. 0.20 newtons divided by the density of water in SI units is 1,000 kilograms per cubic meter. So a cubic meter of water weighs a metric ton. And times g, there's our 9.8 newtons per kilogram. So the volume is a ridiculous 2.041, 2.04 times 10 to the minus 5. 2.04 times 10 to the minus 5 cubic meters. Now, I guess we could have just looked at this and said the buoyant force is 0.2 newtons. That is the weight of 0.02 kilograms. So that's the weight of 20 grams. So then you'd say, well, that must be 20 cubic centimeters. So I guess, you know, we could have just kind of in our heads said, oh yeah, that's 20 cubic centimeters. But actually, right, which is, see, this is 20.4 times 10 to the minus 6 cubic meters, which is 20.4 cubic centimeters. Meanwhile, the mass of the nut is going to be, this is 1.61 newtons, so the mass of the nut is going to be about 0.16 kilograms. So let's divide by 9.8, so the mass of the nut is, so that's 0.164 kilograms. So then the density of the nut, which we think is going to turn out to be the density of steel. So we think it should be something like 7.9 times the density of water. So it should be about 7,900 in SI units. So let's see how that works out. So the density of the nut is, so that's the mass of the nut divided by the volume of the nut. And let's see what we get. We get 8050. All right, so there's 8050 kilograms per cubic meter. So that's like about 8 times the density of water. Accepted values for steel are between about 7.8 and 8 kilograms per cubic meter. No, 7.8 and 8 times the density of water. So like 7,800 to 8,000. So this is in, you know, that makes sense. I think that's compatible within our measurement errors. Remember, after we do this subtraction, we probably only have a little, don't even quite have 2 digits. We probably have like just under 2 digits of information. So this could be 8.0 or 8.1. So that seems pretty decent. Okay, now let's try the same thing with an aluminum object. We'll see what we get. Okay, then, so we're back to reading pretty close to 0. Then we take our aluminum object, and our aluminum object has a weight of looks like 0.33 newtons. Could be 0.34. So sometimes it's 0.3, so let's say 0.335. It seems to be bouncing around between 0.33 and 0.34. So we're going to say this is, and I don't know what you want to call this thing. This is, looks like a little piece of an aluminum flange. Anyway, we're going to call it the aluminum thing. We're going to call it the thing. We're going to call it the thing. So the mass of the thing times g is 0.335 newtons. Maybe we'll say 0.338. The apparent weight when immersed in water is 0.201 newtons. So then we can subtract, and we get 0.137 newtons is the buoyant force. So that is the density of water times little g times the volume of the thing. Okay, so then meanwhile, so now we know the mass of the thing is approximately 0.03 kilograms. We can work that out, getting the decimal place in a minute. And then we're going to get the volume of the thing. So the volume of the thing is going to be this F buoyant divided by the density of water, also divided by G. So that's 0.137 newtons divided by, and here's 1,000 kilograms per cubic meter, and here's 9.8 newtons per kilogram. And then meanwhile, the mass of the thing is going to be this number divided by 9.8, 0.035 kilograms. And the volume of the thing is going to be some absurdly small number of cubic meters at 1.40 times 10 to the minus 5. So that's like 14.0 times 10 to the minus 6. So 14.0 times 10 to the minus 6 cubic meters, which is actually 14 cubic centimeters. And then we'll say, what's the density of the thing? So we hope it turns out to be the density of aluminum. Density of aluminum is about about 2,700 in SI units. So let's see. So the density of the thing is, so that's the mass divided by the volume, and we get 2,467. Too bad it's not 2,468. 2,467 kilograms per cubic meter. So, right, it's like 2.5 times the density of water. I was expecting 2.7 times the density of water. But again, we don't seem to have too many decimal places, so we have some experimental uncertainty. So, okay. You can see, by the way, why when you only have 2 digits worth of information, you don't go typically writing down like 4 or 5 digits, because certainly the 7 is meaningless, the 6 is probably meaningless. It's probably, right, because we think in reality if we had better precision, it'd be more like 2.7 something instead of 2.4 something. Anyway, not too bad though. So before we go on, let's just point out a way to dramatically simplify the math, and that's because we often talk about this thing called specific gravity, and specific gravity is a substance's density divided by the density of water. And in units where you use cubic centimeters and grams, of course the density of water is 1. In SI units, the density is this kind of annoying 1,000 instead of 1. But so if we simply take the weight of the object divided by the buoyant force. Remember, the buoyant force is the weight of the displaced water. So we have the weight of the nut divided by the weight of the displaced water. That gives us the specific gravity of the material the nut is made of. 1.61 newtons of weight of the nut divided by 0.20 newtons of the weight of the displaced water. You just divide those two things, you get 8.05. So there's the specific gravity of steel. Okay. And then we take the other example. We have the weight of the thing, which we think is aluminum. Weight of the thing is 0.338 newtons. And then we divide that by the buoyant force. The buoyant force is the weight of the equivalent quantity of water, and that's 0.137 newtons. So you take 0.338 newtons divided by 0.137 newtons. That's a dimensionless number. That's our specific gravity. And that's going to be 2.47. So again, that's basically the specific gravity of aluminum within our measurement uncertainty. The weight of the object divided by the buoyant force when it's fully immersed. So again, in this case, we got 2.47 for this ratio. So that's the specific gravity of aluminum, more or less. And in the first case, we got 8.05 for the ratio of this weight to the buoyant force, which again, that's pretty close to the accepted value for the specific gravity of steel, which is, 7.9 to 8 roughly.
We're going to take a look at what happens when an object moves in an airflow. And the standard explanation of this is Bernoulli's principle. What we've got here is a hose connected to a blower. This could be the exit tube of a vacuum cleaner. What we're using here is a blower from an air track. So air is going to flow out of here. Right now there's no air flowing and my ping pong ball just sits there. But when we turn the air on, we've now got a column of air coming out of this tube. And if we're any good at this, we can get the ping pong ball to levitate. Now, the stability is an interesting thing. Certainly the air could blow it up, it would go up, and it would just keep going. We clearly have a case of kind of a terminal velocity in that it's risen to a height where the air hitting the bottom of it is delivering the same force as gravity is delivering. But why does it stay balanced on that column? You can see it tries to go sideways, but for some reason comes back to the center. So there's a centering force. And that centering force is based on Bernoulli's principle. If you visualize a column of air here, if the ball tries to move out of the column of air, it moves to a region where the outer edge of the ball is in still air. And so one half of the ball has high velocity air going past it, the other half of the ball has stationary air. According to Bernoulli, the pressure of fast-moving air is lower than the pressure of slow-moving air. And so as it tries to move off-center, there is a low pressure towards the center that pulls the ball back in. Now you say, all right, sounds like a good story, but I could believe it would just sit there based on the balance between gravity and air pressure. So, as with any decent science, this really has to stand up to observation. So what if we don't have a vertical array? What if this thing tilts and we're relying entirely on air velocity? And so I'm going to tilt this over, and please note now, the ball is no longer directly above the nozzle. It's hanging over nothing, which means there must be something going on with trying to exit the airflow. And it doesn't matter whether the airflow is vertical or not. As you can see, eventually we get some stability issues if we push it to its limit. But the faster the airflow and the heavier the ball, the more stable it will be. In other words, the question really is, what are the combination of forces acting here? And a ping pong ball is awfully light, so just a little air turbulence is going to make it pick all sorts of other options. But once again, this is repeatable behavior, and we've now got this ball out there in space, not directly above its airflow.
So you have faster air above the ball and slower air below the ball.
Right, so when the ball tries to drop out, it moves into a slow zone, and the fast zone puts a lower pressure, and that low pressure exceeds the ball's weight and pulls it back in.
So you imagine the streamlines coming out of here and spreading out. The streamlines spread out. So then you get faster and maybe directly in front, and as you get farther out.
Yes, exactly. Yeah, it's not an on-off switch, it's a gradual field. It's very hard to get it to stabilize off-center. And so in general, we stabilize here, and then once it's found some equilibrium, we sneak it over here, and it doesn't know what we did to it. And we're out there in a region that's not directly above the source of the airflow. To revisit the stability of the ball in the airflow, based on some updated thinking, these days, Bernoulli's principle, it's been realized that Bernoulli's principle is the equation is a conservation of energy equation. It works fine inside a closed tube. But when you talk about airplane wings and baseballs, they're in an open system. And the conservation of energy is a harder thing to keep track of. Here at Penn, we had a high-energy particle physicist named Howard Brody, whose hobby, and more than hobby, his avocation was tennis. And he began to direct his physics skills at tennis and ended up becoming the premier authority on the physics of tennis in the world. And Dr. Brody was an advocate of this approach long before it became popular in the journals and the textbooks. Today, this is referred to as the coanda effect, and that starts with a C, C-O-A-N-D-A. And the coanda effect suggests that the effect of a fluid on a moving object is not so much based in an open system, so we're talking a baseball or an airplane wing. It's not so much a Bernoulli problem as it is a conservation of momentum problem. And what Dr. Brody used to say about tennis balls is that if you wanted to know where the ball was going to go, you said, where is the air going? So as the ball moves through the air, the question is, how does it dump the air that's in front of it? The air comes past, and if that air goes around the ball equally in all directions, then the ball goes straight. But if the ball's got some spin on it, it's going to have a preferred direction. And the term coanda relates to the fact that fluids tend to cling to surfaces as they go past them. And so it turns out that this fluid going past the ball is going to cling to the ball and not let go in a straight line. It's going to curve and go off at an angle. And this is clearly what happens with an airplane wing. And so now we say, all right, we had air moving horizontally as it arrived. We have air moving with an upward component as it leaves. So if the air received an upward component of momentum, the ball, in order for momentum to be conserved, is going to get a downward component of momentum. Now, once again, we would like to illustrate this, and one of the better ways to do it, and I apologize for the fact that on video this is not as clear as it would be if you do this in your own kitchen. Just get yourself a fairly large serving spoon that you can hang from a free hanging point. And if you put this in the sink and run water vertically down on the back of the spoon, you will note that the water hitting the back of the spoon, and your first thought would be, if I have the mass of water hitting the back of the spoon, it would probably make the spoon move away from the water. But what you're going to watch happen is that the water clings to the spoon, wraps around, and exits, moving towards the scoop of the spoon, away from the bulge. And so we're going to do that. I'm going to place the spoon here. You can see the silhouette, and we don't have a spigot, but I've got a bottle of water. And so we're going to run this water down vertically. And you note that when the water hits, the spoon surges toward me. And you can see the water leaving the spoon in a direction away from me because of this clinging effect. And of course, this is what happens with an airplane wing. As an airplane wing moves through the air goes over the wing and comes down that curve, goes downward, which gives the wing a comparable momentum upward. And so this is the approach that is generally used these days as an explanation for the lift of an airplane wing or the curve of a curveball as it flies through space. Well, hey. So what we have here is a column of water. We had to give it some color. It's a column of water. The red tape is covering 3 holes in the side of this column. And so what we're interested in is the effect of height on a fluid column. Bernoulli's principle is actually an equation, and it's hiding back there on the blackboard. And as we have alluded to, it's a conservation of energy equation. And it essentially says that you can slosh things back and forth between pressure, height, and velocity. And if you notice, the combination of those 3 variables, if managed with the right math, is going to be a constant. And so what we're suggesting is that height makes a difference here. And if we don't have a velocity, if the third term there has a 0v, this reduces to a pressure-height relationship. And it turns out that the pressure is going to be proportional to the height. In other words, we've got a constant with P and H being involved in its calculation. You have experienced this. If you go to the bottom of a swimming pool that's pretty tall or pretty deep, you notice your ears popping. There's a real issue there that the water starts to weigh enough that it's putting pressure on your eardrums, and your ears are a pretty sensitive pressure sensor. So we've got a stack of water, and the water ends up pushing down, and the more water above you, the more it pushes. And so you're going to have a second atmosphere of pressure on your ears at 10 meters or 34 feet down. Well, it turns out that we think that the pressure of this water is not very heavy right here, and that it gets more pressure in the middle and even more down at the bottom. So what I'm going to do is peel this tape up, and we're going to look at what does this water do. Well, what it does, if we look at our Bernoulli equation, we're now going to bring velocity into the picture. And if we've got more height, then we've got water that when we give up that height, we'll get more velocity. And so the water down here is going to come out. And the interesting thing is, if you sit down and work out the numbers, the velocity that the water will exit the opening down here is the same as the velocity that a stone would have if we dropped it from the top of the water, because it's all gravitational potential energy, whether we're using it with water down here or with a falling stone. And so clearly, if the stone falls less distance, it would pick up less velocity. We will see the velocity manifest as the distance that the arc travels before it hits, runs into the ground there. So we'll add a little water to make up for what's leaking here. And if I'm any good, I'm going to peel this tape up. And we can clearly see that the water at the bottom had the greatest range, and the water in the middle and the stuff up top, we passed that opening pretty quickly, but it didn't come out very rapidly at all.
And by analogy with projectile motion, the range of that parabola lets you infer the initial velocity when it comes out.
Correct. We have a hose coming here that we're going to be able to blow air through. And we have a glass tube here which has been necked down in the middle. And you can kind of see that it's got a dimple there, so the cross section of it has been reduced by at least a factor of 2. So the air will come in a wide section of glass right here. It will pass through a narrow section and then continue out through a wide section. And if you've been paying attention to Bernoulli's equation, you can see it on the blackboard there behind us. You note that there is a velocity term over there near the equal sign and a pressure term. You will also note, and it's not accidental, that we have set this up horizontally. And setting it up horizontally, we have removed the H term. In other words, what goes on in any place here has the same height as what goes on in any other place. And so we're really going to look at the relationship between the pressure of the air and the velocity of the air. And so the equation of continuity tells us quite simply that, okay, if we've got a big cross section, we can move a lot of volume without going very fast. But if we get a narrow cross section, like the rapids in a stream, and what happens at the rapids? The water runs fast because it's not deep. And suddenly the cross section disappears and we got to go very quickly. Because remember, no molecules get in at the entrance unless some molecules leave at the exit. And so to get these guys some room to come in, these guys have to find a way out. And so we can then say that we've got a low velocity in this wide opening, a high velocity here, and a low velocity here. Now down here we've got 3 connected tubes. They've got water in them, and right now the height of that water is determined entirely by gravitational potential energy. And not surprising, each of these guys has chosen the same height, because if any one of them were higher than the other, the gravitational potential energy would have pushed these guys up, they would have come down, and bingo, we're back to balanced. But each of them opens into a separate section of the tube. And so we have suggested that according to Bernoulli, high speeds here lead to low pressures. Low speeds here and here are going to lead to higher pressures. And so we think, if this assumption of the Bernoulli equations is true, that if we run air through this, we are no longer going to have equal levels of fluid, but rather we're going to see the fluid in the center tube go up to react to the lower pressure it senses at the narrow section of the pipe. And so over here I've got a compressor, and the compressor is going to feed air through this tube, and we're going to see what happens. And so here we go, and look, I'm out of the air is moving through the tube this way. So the pressure is on this side, it moves through and exits on the open side of the tube. And so here we go. And as soon as we lower the flow rate, we're back to just a steady state of fluids seeking their own level. But if the air moves at a high rate of speed, we can actually get that fluid to move to a pretty good height. If we pump up the pressure in that compressor, we can actually get this to come so high up here that it gets caught in the airstream and gets blown out. what we have is an atomizer. And this is the way a perfume atomizer works. That you take a bulb, you've got a little container of perfume, there's a tube running across the top, you squeeze the air, the high-speed air draws perfume up, and the perfume gets blown out the side. This is also the way that archaic device of the internal combustion engine, the carburetor, works. Because in that, we draw in the air that the engine's going to use past a tube that goes to a reservoir of gasoline. And again, the low pressure draws the fluid up, and if we design it right, we mix the gasoline, 1 part of gasoline to about 15 or 16 parts of air, and bingo, it burns nicely in your engine. Not as well mixed and organized as if we use a fuel injector. And so the carburetor is no longer used these days because we care about both mileage and emissions. But cars built up until the 70s or 80s all had venturi devices, and that's what this tube is called. It's a venturi tube that relies on Bernoulli's principle to draw fluids into a low pressure area.
Well, what we're doing here is we're using this tiny, roughly 4 centimeter pressure head as a source of, so basically you have density of water times little g times height is the difference in pressure between this water and the atmosphere. So we have a so-called 4 centimeter pressure head. So rho GH is 0.04 meters. That's going to be our pressure difference. And the flow rate, if it's laminar flow, should be proportional to that pressure difference between here and here. So this is going to be whatever, density of water times little g times 0.04 meters. This is going to be atmosphere. It says that delta P. And then it's times the radius to the 4th power of this tube. So this is a tube with a well, it's a 1.9 millimeter diameter. When we have another tube that has a 1.0 millimeter diameter, so it's roughly a factor of 2 in radius. So this is the high radius tube. This is going to be the low radius tube. And let's see. So we expect to get roughly 16 times as much flow out of the big tube as out of the little tube. They're the same length. Now downstairs in the denominator, you have the length of the tube. In the denominator, you also have the viscosity of the water. But it's water in both cases. It's the same length. So the only thing that's going to change here is the radius. So our claim is that by changing the radius by about a factor of 2, we're hoping to see in Poiseuille's law that we're changing the flow rate by roughly a factor of 16. It's not exactly a factor of 2, so it's not going to be exactly a factor of 16, but we're going to see if we're in the right neighborhood. So we are using a scale here to measure grams of water that we collect. And then we're recording the data with a computer, and then the computer is going to measure the slope. It's going to tell us the flow rate. Now we really want cubic meters per second for SI units. This thing's going to tell us grams per second, and we're going to then divide out the density of water, and we're going to put it into SI units, and we'll get some extremely small number of cubic meters per second. Okay, so here we go. Okay, are you ready? Okay, so we're going. I mean, see, this is about the fastest we can go for it to stay laminar.
Right.
And the other one's even slower.
Well, it's laminar through the tube, I think.
It's laminar in the tube. It's dripping because it's got to build up to a drop that weighs more than the cohesion. Right? Like that's, because I had the same question in my head.
Yeah, so that's how you'd see it flowing.
But it's not dripping inside the tube. It's dripping at the end of the tube. Because it's such a tiny amount that it sticks to the metal with more force. No, I just meant we're gonna time it, you know, it stops at the end of the graph.
Oh, okay. I guess that's actually just right.
It's a race, look. 117, 118.
Okay, there we go.
How
So
about
now,
that? It stopped before 120.
Yeah.
okay, so we can measure the slope and then put on the smaller diameter tube. Yeah, see if you can figure out.
And which one is this?
Okay.
All right, so I blew this up so it's legible,
Okay.
right?
Oh, so actually while you're there, let me just zoom in for a sec on the screen. Okay, so that was the result.
see it?
Yep, oh yeah. So, okay, so that was 0.4364 grams per second. 4364?
4364, yes.
4364 grams per second.
And this next one will be low, right? It's-
Yeah, oh, it's gonna be a lot lower.
So I'll move this out of the way. Here it's running.
It's running? Okay, here we go, here we go. Yeah, it drips so slowly.
So we had to
So here we can
cut
zoom in and
piece
see.
of vein out of the calf and insert it. Pete's got some outlandish combination of little plastic tubing layers to close up all these, match all these hole sizes. And we had to pull that back together.
I'm measuring milligrams here. Okay, those are very different slopes.
And it's telling me 0.04028.
4364 divided by 0.04028. 10.8, and our prediction is 10.2. I would say that's pretty darn good.
Wow.
Nice. Okay, and okay, cool. I think that's pretty neat.
That's as good results as I've seen.
Yeah.
And I think your Reynolds number calculations are critical. Hi there. We've got a gadget here. We kind of made our own tom-tom. We got a piece of truck inner tube stretched across a trash can, and I can hit it not very, I'm not going to get a job in the Philadelphia Orchestra with this. If you take a look at the trash can, here it is. It's just a great big Rubbermaid monster trash can. But if we swing it around here, so what's happening? We could model this in many ways, but it kind of seems as if we're getting air to come out of this hole and to come over here and move these styrofoam cups. And, you know, sounds good. But if we're going to do decent science, we ought to be able to experiment with this. This is a model that could be tested. Our problem is we can't see air. Unless we tag the air with maybe smoke. So let's do that. So there's some smoke.
I almost don't reach.
So instead of having the smoke outside of the drum, we're going to put the smoke inside the drum. And let's just see what happens first. Oh, is that cool? So we were right. There's a plug of air moving when I hit this. So here's my hammer, and I'm beating the drum back here. And that plug of air is better organized than you thought, isn't it? What if we shoot it right at you? Are you paying attention now? Oh, that's pretty cool. What other letters of the alphabet do you think I probably can't make a Z, can I? No, we're going to have to settle for O's. And we'll talk about those O's in a minute, but let's see what happens if we aim our now visible. Well, okay, we'll put a target up here. Here's a plastic bag. Okay, we can see where our projectile goes. Ooh. So this really is a neat thing in that you kind of thought of air as a continuous quantity, but this is a discrete lump of it that seems to be moving. So let's go back to the cups briefly and see if we can observe this happen with our projectile made apparent. And so it's almost like a bullet. Ooh. So notice what's coming out of here. What's coming out of here isn't just a random lump of smoke. Look at that guy right there. Ooh, if I'm any good, I can like catch one on my finger, right?
At low speed, it's really impressive.
Yes, and so look at those babies. You can blow smoke rings without getting lung cancer. This is a major breakthrough. And so those rings are something called a vortex. And what's happening is we're firing air. We're compressing the air in here. It's coming out through this tube. And because it has to pass the opening of the tube, there's a speed difference between what's down in the center and what's out near the edge. And that means that the center stuff is moving faster and we get a rotation. We get a vortex. There's a ring of air that is different than the air around it. And that's our plug of air. That's our vortex. And it's forced out, and because of its rotation, it maintains its stability.
Are there any familiar examples of vortices when you look up at the sky?
Well, among other things, we have the gas and air, or the air that leaves moving vehicles, and most particularly when airplanes are flying in the upper atmosphere. They are leaving what's called a contrail behind them, and that is a trail of vortices. And what's going on there is the gases from the engine exhaust and the pressure change related to humidity is causing condensation of water to give you smoke just like this. that lets you see the vortex. And that trail runs along behind the airplane. Conditions have to be just right. Every time you see a plane, you do not see a contrail. But on a bright sunny day, you may look up and see that white line of cloud following behind a jet plane. Used to be when you drove down City Avenue in Philadelphia, they had steam pipes running under the road, and in the winter, there would be steam coming off of the road, and you'd see vortices behind the cars as they moved down the road. We no longer have that wonderful wind tunnel physics opportunity in driving in traffic in our city. But vortices occur in many places and are critically important to understanding the behavior of aerodynamics in everything from meteorology to designing airplanes. So this plug of air, we earlier spoke about the behavior of fluids moving past objects. And so if we take two, and we'll move this so it's a little easier for you to see the separation. So we've got two cups that are separated, and now you're all believers that we're sending a plug of air out, and if we aim correctly, we can get that plug of air to move through here. And we spoke earlier about the Bernoulli effect, which says that fast fluids, so we spoke earlier about that Bernoulli effect. It said that fast fluids have a lower pressure than slow fluids. So there's going to be a moment when there's a fast fluid moving through here and a slow fluid over here, which means the pressure is going to go down in the middle. Your first reflex would be to say, well, if I run something through here, it's going to push these guys apart. And so we're going to see, does the Bernoulli effect overcome the simple getting out of the way problem? So let's see how well I've aimed this. And we want to move over just a little bit. Thanks to the smoke, we can kind of see what we're doing. We'll get there.
Oh, nice.
Okay, and so now we're drawing them together because we're shooting right down the middle. And what do we got? We want to get your contrast to be good. So let's set that up again. It seems like we've got it aimed well. And so we do seem to be able, but if I hit one straight on, we knock it off. And so that fluid effect of velocity versus pressure is there. That was kind of a dramatic one, and they bounce off each other. And so we can actually see that take place under this circumstance. So this is kind of a neat tool because once we tag the air and we get the smoke showing, we can actually see where the moving air is and take a look at how it influences things around it.
Wow. That's beautiful. Do it again.
Yeah, I think we do better with just white light here, huh?
Yeah.
It's almost like you could box these things and sell them.
One thing I'm not sure is obvious on the camera is the spinning motion of the vortex.
Right, and see, I would almost think you want to bring it. Okay.
That's cool. Yeah, I like to be able to see, you can see the spinning of the vortex. I think it's also cool if you're going right at the camera and you see it spinning.
Right. I mean, Mary may have
Yeah, do it again.
a point of view.
Yeah, do another one.
Oh, okay, this is your flat plane.
Yeah.
Okay, so what do we,
So the idea is, do you want to aim it at catching it or not?
I see. I thought you might want to catch the plane perpendicular to me.
right, but you'd have to scan pretty quickly. But I'll tell you, that dot moves.
Yeah, I'm like trying
You're
to.
saying it's too big to be.
What? That is actually really cool looking though.
Yeah, poof! Matter, antimatter.
I know that.
I'm creating anti-vortices, and
Absolutely astounding.
they're disappearing when they hit air. Yeah, we almost have too much smoke there. Yeah, there. Okay, that's good.
I'll be right back. I'm gonna go get my phone because I want to catch this.
Okay, then another. Try the rings now.
Yeah, and see, that shows up. Now what?
Try that. Oh, that's kind of cool.
Yeah, it is.
You kind of see it travel along.
Yeah. Oh, I tell you, it's really cool looking from my viewpoint.
Yeah.
It looks like a hockey puck running out to Bill.
Which kind of negates the effect that we want them to see.
Right, because we don't get the vortex, we just get the section of it. Yeah, there's that.
What if you make a slow one?
Yeah, that's what I'm. Huh.
I almost feel like we need something that will disperse the laser in both directions.
Well, you know, the old, those laser projection things where you have the mirror that's oscillating.
Yeah.
So you almost get a video sweep. So the laser, in essence, fills the space faster than the eye, you know, in less than a 30th of a second.
Yeah.
So then you could shoot your smoke across it.
What
And
about if we just rotated another one of these apertures onto that?
what do you get? I don't know. You may not be too far, but this might be worth it, Mayor. Yeah, I was thinking of a diffraction grating, but this is more like a. I mean, they've done this so you don't really see orders. You know, yeah. What diffraction orders? You just see one full smear. It's almost like a barrel lens. You got one?
Yeah.
See, there you go.
Oh,
Because looking along the lines of the light really,
Oh, that's great.
try to walk over a little more and let's see whether,
Oh, now if you're aiming toward the camera, that seems maybe even a better effect.
see the sight lines, when you look into the light, you get the strongest image of what the laser is doing in the smoke.
Yeah, actually, Mary, maybe if the direct light from the laser is going a little bit away from the camera.
like that?
Yeah, or like if you stand closer to the camera and aim the laser a little toward the source.
What do we get there?
So you want me to stand by the camera and aim towards Bill?
Let's see. So yeah, exactly. Yeah,
Okay.
try that. See, so then you don't get the direct light. Oh, that's pretty good.
Yeah. We gotta, that whole backlighting thing really does it.
That's pretty good.
Now, you know, like, you can kind of, ooh,
That's a good.
yeah. So we almost need to just get an eclipse device, you know? Oh man, look, some of that's really good stuff. Wow. Oh, look at those secondaries.
Yeah, I wonder what explains the secondary.
I think it's echoing. You know, I think it bounces off the front, comes to the back, and we get a second ripple.
It's a pretty long time. Yeah,
Yeah, but this is clearly not moving at the speed of sound.
right. The speed of the air movement.
Yeah.
That makes sense, actually. Yeah, it seems compatible with the time it would take the vortex to cross the tube.
Right.
Yeah.
Yeah, that,
Pretty cool.
wow. Look at these guys. Oh, man. 3. Yeah, look at that little third one coming out. I mean, this is just sloshing around like a bathtub.
Yeah. Sloshing is probably the right word for that mode. Yeah.
Yeah, and when you hit it hard, you have so much crap going on, you can't see the secondaries. That's really cool.
Yeah. Okay, then. Oh, now before you hit that too hard, let's see if we can make it really. Oh, I know.
Oh, that's nice.
That's pretty good.
Yeah.
You don't need marker really to show that the cup's moving, because you can see the
Yeah, it's
label.
in the frame. Projectile. I mean,
Right here you just see it splash through the plane.
right, like you don't get any sense of momentum there. See, whereas here, look at that.
Oh, if you had two of these. Well, that's kind of cool.
That is.
Try a slow one. Oh, I can make them perpendicular.
Yeah. So what we were seeing, Mary, with his flashlight in place of your lasers, I was hitting it really slow, and we would get the primary, and then we would get a second and a third as the air was sloshing in here. But you do it really light, so you don't have so much smoke in the first shot that it obscures the second.
Right.
You know, but it was really interesting.
Oh,
Wow.
that's pretty cool. Right?
Yeah, here, here, look at these 4.
Wow. That's gorgeous.
Isn't that something?
That's like, have fun.
Wow.
That's beautiful. Do it again.
Yeah, I mean, I think we do better with just white light here, huh?
Yeah.
It's almost like you could box these things and sell them.
One thing I'm not sure is obvious on the camera is the spinning motion in the vortex.
Right, and see, I would almost think you want to bring a camera right down here.
Yeah. Harbor Freight.
Okay.
That's cool. Yeah, I like to be able to see, you can see the spinning of the vortex. I think it's also cool if you're going right at the camera and you see the spinning.
Right, I mean, Mary may have
Yeah, do it again.
the point of view.
Okay, so I got 2 videos here that might be worth it. Oh, I'll get out of the way.
Yeah, some of these, boy, you really get like outer and inner surface detail.
Kind of ghost-like. So, oh, now look at that. Oh,
Wow.
that's cool. You can really see the vorticity.
You've got some rotation.
Yeah.
Alright, so I don't know if that actually airdropped to you, so I'm also going to text.
Oh, I see. So let's see what happens when you
If you go this way.
I love that there's a text group in my phone called Bill and Bill.
Bill and Bill. Bills.
Now, Bill, what if we give me the light for a sec? I was just wondering, can we?
Right, it's a question of like, how do you get enough light on the smoke without having too much light in the camera?
Yeah.
Oh, look at that one.
I think this machine is described in the Feynman lectures, the second fluids chapter.
Really? In what? In fluids, you said?
I think he has he has dry water and then wet water. I think it's his wet water chapter.
Uh huh. Which volume? Is that 1 or is he in 2? Well, no, 2 is E&M and 3 is quantum, right? So it's got to be 1.
Sorry about me.
Oh, you're dropped.
Finally! I didn't hear it work, so you're also getting it via text.
That's the airdrop sign. Okay.
It just won't let me send this other one. But hopefully you'll get 2 things airdropped that way. Let me try it this way. Okay. Slow-mo one isn't working, so hopefully it airdropped to you.
Oh, slow-mo. Cool.
Yeah, so this is the slow-mo one. And I feel like the very first one in slow-mo is like here.
Nice. Yeah.
And there's a couple other good ones that come up, but it's like excruciatingly slow. Once it's slow, kicks in. Oh, did I hit pause? Oh, that's what missed it for. Oh, here we go. Here's another one in slow-mo.
Oh, yeah. Oh, wow.
Yeah, that's cool. Cool.
So it'll be excruciating to go through, but you